So, it's so cool to finally be here at Insomnihack again after 2 long years of waiting. A question for you. Who of you is a CTF player? Please raise your hand. Very nice, very nice. Who of you likes to do reverse engineering and solving crack myths? Even better. That's so awesome. So let's dive in and solve a Warmy Crack Me challenge. Oh no. This doesn't look good. This doesn't look good at all. That's dreadful. So, while that control flow graph before was really scary, my goal for today, after this hour, is that if you encounter something like that in a CTF or in the wild, it won't be as scary anymore, because you know how to apply symbolic execution. My name is Jannis Kirschner. I'm a Swiss cybersecurity researcher, CTF player, and today I'm not affiliated with anyone, so just my opinions. So let's look at the roadmap. First, we start with the problem state. When do we use symbolic execution? Why do we use symbolic execution? From which we're going to branch off and look how those systems work under the hood. And finally, we'll get our hands dirty and look at anger tricks and how to apply it in a CTF. Connection seems weird. Here we go. Yeah. Better? Wonderful. So, why do we use symbolic execution? And to illustrate that, we're gonna solve a crack me challenge from a CTF from 2 years ago, which is a perfect example because we can apply all those techniques. So when we first look at the crack me, do some initial static analysis, we see it just takes some values from standard input, it passes them to a check flag function, which evaluates your input, and based on that, it either says, hey, you solved the challenge, or no, you didn't solve it, and the fictitious robot in this example here stays asleep. So how can we approach that? The first idea, can we brute force and just solve another challenge while have that run in the background? No, that won't work because the input is very long. So we're gonna have to solve it manually. When we look at that check flag function, we see it takes our input and it applies many constraints to that. It has a lot of assumptions about our input that needs to be valid in order to return true and in order to say, hey, that's the correct input you submitted. So we take those assumptions and we put them in a file, in a spreadsheet, whatever you prefer. Those are a lot of assumptions. And then, on a piece of paper, we can try to solve them. We start with the simplest one, like static assignments, like some calculations, and work our way to the more complicated ones. This is not very reasonable, especially not in a CTF. It just takes forever. We can do better. We can do better with SMT solving. A great example of an SMT solver is Microsoft's SET3, which can determine if a mathematical formula is satisfiable or not. And it builds the basis for most symbolic execution frameworks. How does it work? Let's do a logic puzzle. Imagine you're stranded on a deserted island and a storm brews up and you're trying to seek shelter and you see this big castle. There are 2 people in front of the castle that say, hey, we can let you in if you solve our puzzle. So there are 2 kinds of people in that island. The knights that always tell the truth and knaves that always lie. So you have those 2 people in front of you. One is called red and one is called blue. And blue tells you we are both knaves. Can you figure out which of them is the knight? Any ideas? I'll show you the solution. It must be red, because blue cannot be a knight if we apply our logic. If blue would have been a knight, he would have told a lie, which is unfeasible since knights cannot lie. And this is just what an SMT solver is doing under the hood. We gave it a formula and it tries to evaluate, is it satisfiable by that logic? Can it return true? Or isn't it? There are two kinds of those solvers. There's Boolean satisfiable theory solvers, which just fill in ones and zeros to try, is it satisfiable? And there's a little bit more complicated SMT solving satisfiability modular theories, which can even put in new formulas, integers, strings, new functions. It's really cool. So basically, SAT solving is the simple one with propositional logic, and SMT solving builds up on that, but with more intricate input. How do we do that in practice? We install set3, and please install the set3 solver package, because if you're going to install set3, it's going to be a tool for ZFS to S3 bucket something. Definitely not what you're going to want to do for your CTF. So set3 solver. Then it's very simple. You define a key space for your input, and you instantiate the solver, and then you're going to fill in all the constraints that we've extracted before by hand in Python. All the constraints, and then you can check, are they satisfiable? And if they are, you can concretize them and get a value back, which in this case would be the flag. You can hear I'm not that excited about that solution because extracting all those constraints take forever, and especially in the CTF where time is everything. So we can do better. 100 lines of code, 91 constraints, lots of constraints for the code. So, if we're going to apply symbolic execution, do we have any guesses to how many lines of code we can reduce it from around 100? 1 line, possibly, but I say we can do about 4 if we like clean code. So this would be the exact same solution for the exact same challenge, just with symbolic execution. What all this code is doing, we're going to look at in the Angular hands-on part. So let's compare them. Brute force is infeasible. The computation just takes way too long. Solving it by hand, a really, really long implementation time, but it could be done. We have reduced that via set3 and have a long implementation time with a short computation. And we have even reduced that by applying symbolic execution. So, how do those systems work? Imagine you have a certain state in a binary that's interesting. For example, you have some code that's been deobfuscated, you have a binary state that's unpacked, or you have, like in this case, a crack me that has a solution which says, hey, the crack me is solved. The symbolic execution tries to match those binary states to an input. So it can visualize we can visualize your binaries as a tree with your basic blocks and the branches. It walks those and it matches binary states to input. Let's look at the concrete execution. This is what you're going to do if you just enter a program. Normal program run, how you would do it in your shell. You enter some value, the value gets evaluated, and based on that, it prints, it works. Or if you would have entered something higher, then it would have executed the crash. With symbolic execution, you're not providing a concrete value, but a symbolic one. This works better. So you provide a symbolic value to your input, and it evaluates both parts of the branch. It keeps track of both states for your branch, and it keeps track of the constraint. In this case, that size, your input, has to be smaller than 5. If at any point your binary terminates, either via a crash, either via normal termination, it takes those constraints it has accumulated over time, and it solves them via an SMT solver. So you get a concrete example back. This poses some problems. For example, if you have a loop, and your loop depends on a symbolic value, on the symbolic bit vector, it can happen that it never exits the loop, because it's hard for the symbolic execution tool to reach deep into the trees. And therefore, there's another technique, which is called concolic testing, which is just a mix between concrete testing and symbolic execution. We can regard it as seed-driven symbolic execution. So while symbolic execution systems just walk all of your binary, usually with the DFS algorithm, you can change that. The concolic execution first concretely executes, and based on that concrete execution, branches out. So in this case, you never have problems that you can't have a termination, because it has to terminate at one point. How does it work in code? We provide our input concretely with some random seed. It gets evaluated, and it executes the printf. While it has executed concretely, it has still accumulated the constraints, in this case, that your input has to be smaller than 5, and it inverts them. It inverts the last accumulated constraint, and that way, you get access to the other side of the branch. And from there on, it can, for example, explore the crash function. And it does that with all of your constraints. So it takes the last constraint, it negates it, explores, goes back to the last constraint, negates it, explores, until there are no constraints left. So if we compare them, we have the solid, the concrete approach, which is very, very labor intensive for not a lot of results. We have the more liquid approach that needs a high amount of computation. And we have our slushy approach, which in this case is concolic execution, best of both worlds. There are a lot of different frameworks, a lot of different tools that you can use to achieve that. Let's look at some of them. The sQuery is a very cool tool. It was developed by EPFL, as far as I know. And you can use it to symbolically analyze whole systems. So if you want to symbolically analyze a device driver, or if you want to symbolically analyze software with lots of complex interactions, it's probably the tool of your choice. But the downside is, it's very hard to implement. There's like a lot of stuff you need to consider. It's a lot of code, and it's probably not the best solution for your run-of-the-mill CTF. A better solution for that are user-level tools. For example, Angular, Triton, or Manticore. They provide a great mix between convenience and speed and instrumentability, and are really cool tools for your CTF. The workflow is a lot smaller, is a lot more realistic to implement them. The code is a lot smaller as well. And finally, there's also code level symbolic execution with tools like CLE. So if you have access to the source code, or you clean some decompiled code up, and you just want to analyze a certain function, you can compile it with CLE. It's LLVM based for C functions. And yeah, then you can symbolically execute your custom compiled code. This is really cool because you don't have to do a lot of work. You just have to mark your variables as symbolic. You can put some assertion in it, and basically you're done. But the downside is that you need to have access to the source code. So not a lot of code. As you can see, there are lots of different tools for lots of different jobs, but generally the Angular framework is best for CTF. Let's recap for a second. Symbolic execution tries to match input to binary state. It traverses an execution tree. It accumulates the constraints of a path, so what you will put in an if condition, for example, and it solves them using an SMT solver to get a concrete output back. Concolic execution builds on that by first driving it with the seed and then branching out for that. So you have higher performance. The downside is you might lose some coverage because symbolic execution explores all of the system given enough computational resources, while concolic execution has more of a fuzzing approach. And there's a lots of different tools for lots of different jobs. You might want to use Angular, which we're going to look at now. How convenient. Angular is really cool. It has a Python 3 interface. Who doesn't love that? It has been used in countless CTF. You can reverse with it. You can build ROP chains with it. It has even been integrated into fuzzing tools. It's really convenient. So, Angular workflow. You've seen this before. We had lots of code. We reduced it to not a lot of code. You also seen this before. It's the user mode workflow for symbolic execution, which we're going to look at in depth now. So first, we want to initialize the program state. We want to get our input, our symbolic input, into our target. And this is some code for the query that we want to solve. So it just takes some values from standard input, puts them into a buffer, evaluates them, and based on that, it either says, hey, the binary is solved, or hey, the binary isn't solved. So next time I'm going to use Windows, I swear. So we initialize our project. We can put in some load options. Let me try something real quick. Maybe this is better. Okay, we can provide some input. In this case, we initialize the project. We can provide the base address. We can provide if we want to load external libraries, stuff like that. Then we initialize the simulation manager. This is important because this is the component that will explore all of the tree. We can provide a target address, the address where, for example, a solve string is being shown. And finally, we can print out the concretized result, which usually is the flag. By the way, I'm going to release the slides afterwards, so you can just copy the code. It's really convenient to have some boilerplate Angular code for whatever CTF you want to play. This was like a really, really simple example, and this is why I picked the CTF, the Z3 robot CTF challenge. But there are sometimes a bit more tricky ones. For example, if you have a complicated time waste function before your actual code, which just is there to mess with you. So imagine there are lots of code in there, or long sleep functions, or something that's completely unrelated to what we actually want to explore. We can mitigate that by adding a start address where we want to start our symbolic execution. This is cool for functions that want to waste time, for bypassing glibc setup functions, or if you want to define custom input. So by now, we didn't have to define input because Anger automatically tries to provide input for your binary. This works great with simple input, but as soon as it gets a little bit more complicated, we're going to have to do that by hand. For example, with complex format strings, with multiple parameters, or if it's over memory, over file, over the network. And for that, we have a data structure called the symbolic bit vector, which Anger uses for the storage of its symbolic variables. You can just instantiate it with a name, which Anger internally uses to reference it, and with its size. And you can put it into registers, into memory, argv, onto the stack, whatever you want. So let's look at an example where we don't have to provide one password, but two. In this case, we set our state right after we would have provided our values normally as a user. Then we initialize the stack, define our password bit vectors. We align the stack pointer for our new password bit vectors. We push them onto the stack. This is really just like coding basic assembly. And then finally, we run the exploration algorithm. And then we can solve the bit vector if a solution has been found. So really easy, we just set our input after, we just set our starting address right after providing the input. We emulate the stack frame and we solve and concretize the output. Very similar is the symbolic file system. Imagine you don't provide your input over standard input, but over a file. This can happen in a real world situation or in a CTF. And the approach is pretty similar. We set our starting address after the input gets submitted. We define symbolic memory. And now comes some boilerplate code. We add our password bit vector to the symbolic memory. We add a symbolic file. We define the symbolic file system and the simulated file. And we solve it like this code you're probably gonna write one time or copy one time and just change the parameters of it. Yeah, it's just important that after you have an exploration and after a solution has been found, you need to concretize the bit vector. But still fairly easy. As we said, we set our input right after getting the state. We emulate the file system and we solve and concretize the output. Now we know how data gets into the symbolic execution framework. Now we have to define a target. What do we want to achieve? Where do we want to explore to? And therefore, we can just define an address. Pretty simple. We have some solved function, some string, whatever you want. However, we can also enter target conditions. So we can say if a string like solved gets written to standard output, we have found a solution. So we can also search for that. So now we have most what it takes for most challenges. Like you should be able to solve most simple symbolic execution challenges. But sometimes it's a bit more tricky, especially with big binaries. And there you have to define a void state. So a big problem with symbolic execution is that because it takes both sides of every branch, you're dealing with exponential growth. And this can cause state explosion. So just a massive amount of data that you have to search through, that you have to concretize, that you have to work with. And this slows down your progress a lot, especially with big binaries. But fear not, you can just exclude addresses or exclude the data in standard out as we did before, provide it to the symbolic execution framework, and it will try to avoid it. This works best if you manually reverse engineer the binary, if you manually cut out paths that you're not gonna need. It's really cool because you can, that way you can guide your symbolic execution framework into the direction of where you actually want to search, instead of exploring every other stuff that you don't even need at all. So a big challenge I had when starting out with Anger was that I had no idea what's going on. It's hard to debug. I just didn't find out where my issues were. And so I came up with a strategy. I found a way how you can export code coverage, which you can simply load into Lighthouse. You can explore the bottlenecks, and you can fix them by, for example, avoiding states that get executed that take up a lot of unneeded time. How do we do that? There's a step function. It's basically a callback for the exploration algorithm. And I call it this nice function that visualizes and exports the code coverage. In this case, it visualizes what input is provided to Anger right now. It found a solution. And we're going to look at the coverage. And we see we have basic block coverage that has been exported, which we can load into Lighthouse. So that way you can see what instructions have been hit. And if there are unneeded instructions, unneeded code, you can just avoid it. And guide Anger into resolving the issues, the performance issues that you are experiencing. So this already helps a lot. And another thing that helps a lot is limiting the constraint space. So in CTF, you often have implicit constraints. So to solve it, you just have to import the constraint solver engine. In this case, it's a Claripy, another packet to import. Then you have to create a bit vector. For applying manual constraints, you always need to define your own bit vector. It's pretty easy. In this case, just over argv. And then you can apply constraints. In this case, only print out the human readable characters. It's the case for most CTF, and it helps the framework to be a lot quicker because it doesn't have to evaluate anything, just the human readable stuff. Or if you know that your solution will start with a certain flag format, you can apply manual constraints that it has to start with that specific flag format, and also save a lot of computation time. Afterwards, you can just explore it as known and finally evaluate it. So it's really helpful for your CTF to, especially the only printable characters constraint, helped me in the past a lot. So Anger, in its essence, is an emulation framework. And as you might know, emulation frameworks and low-level stuff doesn't like each other. So sometimes if a lot of low-level stuff is being called, you have to use a simulated procedure. It's very simple. It just overrides the emulation with some custom Python code that you can submit. So you can basically write the emulation yourself, or you can, if you have some complicated crypto stuff, you can make it always return the same values and see how they interact. There's lots of approaches you can take with simulated procedures. So you just define a new function, you hook the symbol, and that's about it. If that's too expensive for you, if, yeah, a lot of code to write, you can also use project hooks, user hooks, where you just specify an address, you specify how many bytes you want to overwrite, and then afterward, you just specify in Anger's pseudo Python assembly what you want to do. In this case, we just set a register value. Also very quick and simple to implement. And finally, we can retrieve our results. So usually you want to dump standard input that has been provided, or you want to evaluate your symbolic bit vector that you have injected into memory, as we have seen before. So those are like two main ways to, based on what the binary expects, to get the input to get your flag. It's very simple. So this was a lot of information, I know, and you really should look at the slides again, look at the code, look at some examples. But first you can have a cat picture. Anger also has some limitations, like all symbolic execution frameworks do. For example, if the control flow is non-deterministic, if you have a lot of concurrent stuff going on, so if a function based on its input can't really connect differently, then it's going to be difficult to figure it out with the symbolic execution framework. State explosion is also a really big problem, but we learn to deal with that by avoiding, by hooking, so lots of ways to deal with the state explosion. And you can't inverse your hash functions, unfortunately. Like, it would also cause massive state explosion to try and break crypto algorithms. It won't work for that. However, we can improve performance somehow. A great trick I like to use is to enable the very testing flag. It's so cool because it's so simple. You just have to set one flag before defining the project. And then an algorithm automatically tries to reduce state explosion by merging states that the binary thinks, hey, those paths basically do the same. So it merges them together and we save some speed. Anger also advertises that PyPy would slow it up to 10%. For me, it only slowed my computation down. So I profiled it and it's actually way slower on my machine. I have no idea why, but just take the PyPy with caution, test it on your machine. Maybe it's faster, maybe it's not. So to have great results with Anger, first, avoid all unneeded code. Don't load unneeded shared libraries. Use simulation procedures and hooks where applicable. Use very testing. It's also cool. And maybe use PyPy if it's faster for you. Anger can also be integrated into your workflow perfectly. There are lots of tools that use it under the hood. For example, Anger Management, which is the official GUI for the Anger Symbolic Execution Framework. It's really cool because you can disassemble with it. It features pseudocode, and you can apply symbolic execution straight from the GUI, which is really helpful. There's also Angry Hydra, which is the same thing, just as a Hydra plugin. So you can mark some states that you want to explore, you can mark states that you want to avoid, and you can solve them straight from Hydra. If you're into vulnerability research and if you're into fuzzing, you can give Driller a try, which is an AFL extension with symbolic execution. So if AFL at any point sets the AFL is stuck flag, doesn't really find new paths, then it's going to use symbolic execution to try to drive and find new code coverage, which is really cool because you can explore more of the binary to have a greater chance of success in finding interesting crashes. And finally, there's obviously anger for your favorite disassembler. I strongly suggest you to get hands-on with Anger, to get your boilerplate code ready, to try it out yourself. And a great resource is Jake Springer's Anger CTF, because they provide a lot of CTF challenges, small CTF challenges, specifically for Anger. So you don't have to reverse unneeded code. You don't have to figure out what the challenge is about. It's just about Anger. And they even grouped it into specific Anger themes. So you can, for example, try the symbolic memory. You can try the symbolic file system stuff. So lots of different challenges that you can get hands-on and learn more about how Anger works. Oh, I think it's time for a crack me again. We've seen that before, but it's just not as scary anymore, is it? Yeah, we can simply build a symbolic execution harness. We can continuously monitor and improve the performance of the symbolic execution, for example, by avoiding unneeded code. And finally, we can run it and retrieve our flag. I think it's time for a small demo. Demo gods, please don't fail me before, what? A bit too early. Let's see. So, we have our target crack me. And here's the structure. It takes some input. It passes the input to SymSolveMe, which just evaluates based on constraints. And based on that, it either says solved or bad password. I prepared a small Anger harness, which is really simple. It just searches for the solved string in standard out. And on each step, it visualizes it, so it's a bit more interesting for you. Let's run it. And we found a solution. Thank you for watching my talk. So, as your next steps, you can download my slides from my GitHub. I will put them online real quick. Then I recommend you to walk through Anger CTF, look at all the different binaries, get your hands dirty, and finally, pwn all the CTFs. Are there any questions? Anything that I can clarify for you? Anything you're interested in?
So I'm interested in the ways you can hook up, eliminate states and speed up the execution, because when you're solving a challenge in this way, I imagine that the computation can take a long time, and I'm wondering whether there's any way to incrementally add hooks that improve the performance without having to restart your solution and throw away the computation you already done.
Yeah, I get what you see. I'm not quite sure if you can export the coverage you have so far. The only thing that would come to mind right now is exporting the coverage. So you have it somewhere. And if you see that it obviously hasn't led to a result, exclude it by avoiding it. That would be the approach that you could try right now. But yeah.
Okay.
Other question?
Thanks for the talk. Was a nice topic. My question is about anger, because I feel like this symbolic execution framework, you lose all the control over the execution. So you just give 1 point to start, 1 point to finish, and you start running. But in other frameworks like Triton or Miasm, you control, or at least you can see how symbolically is executed your program. It's true that, for example, in Miasm, you cannot apply constraint solving with C3, because you should do it as another step. But I feel like with anger, you are out of what symbolically is executed. Is it possible maybe to see how everything is executed, or how it applies to improvements in the intermediate code? Yep.
You can control it somewhat, so you can choose the exploration algorithm. So if you want to use DFS, BFS, or some mixed algorithms that they provide, and if you want to see what's going on, you can visualize the state. And as I've shown before, via exporting code coverage, you can see a bit more what's going on. But yes, generally that was, before I figured out the trick, that was a problem in Anger.
Thank you very much.
Thank you for the talk. I really enjoyed the trick with the lighthouse, which helps the visualization. But during the very complex challenges, which are, for example, multiple stage packers, and then you want to apply Z3, and you wouldn't want to waste time reconstructing your executable, do you know a way in which you could save a snapshot from a debugger, for example, from x64, and load the entire state, including all the stack, all the registers? I know the libraries might be a bit hard, but Anger can deal with that. Do you know something that will do something like that?
I think that should be possible. Like, there's a lot of loaders for Anger, like all kinds of architectures, including brainfuck. So I think it should be a solvable task. Under the hood, it uses VexCR for lifting this stuff. So maybe you could write a custom lifter that just reconstructs the state that way. This would be the first solution that comes to mind.
Okay, thank you.
Of course.
Other questions? Okay, so thanks again for the talk. Sorry.
It's more like of a provocative question, but out of your experience, would you actually say that is really true that these solvers help, or people which says I just put in a fuzzer and like a kid typing and I find vulnerabilities and that's all?
They definitely do help, especially like if you compare it with fuzzer, it can be used to extend fuzzers. For example, the Driller framework is open source. And it has been used to find real-world bugs. I also, from what I know, Microsoft internally has a fuzzer called Sage, which is built on concolic execution, which also seems to enjoy great success there. So it definitely is a symbiotic relationship between fuzzers and symbolic execution.
Trade-offs, as always. Thank you.
Other questions? Okay, perfect. So this time, thanks you.
Thank you.
Thanks, sir.